exactly what power. He's got the Steve Jobs, just one more thing. Down pat. Yes, thank you. Now, before I introduce Dave Hurst, the New Space Chicago co-founder and CEO of Orbital Transports for tonight's presentation, the coming economy and space resources, I want to remind everyone of our next month's event. Just do a placeholder for Thursday, November 14th. We've got a couple topics we're trying to finalize, but we've got the space reserved, and we'll be having an event here a month from now. So put it on your calendars and watch for the announcement of the event. And otherwise, thank you for attending again tonight. And now I'd like to introduce Dave Hurst.
Thanks, Steve. Well, good evening, everyone. I have something to admit, actually. I was up until 4 a.m. last night working on this because my computer crashed at 2 a.m. and I lost like most of my work, so I had to then recreate it. Anyway, so if I seem a little loopy, that's why. So a couple of months ago, at the beginning of June, I attended a conference called Space Resources Roundtable. And this was a gathering of pretty much everybody in the world who is working on space resources. And it was just an amazing amount of information. And so I thought it would be interesting, shall we say, to share what I learned at that conference with you all. So that's what kind of led to this presentation being put together. So in April of 2012, Planetary Resources announced their formation, and they would be focusing on extracting resources from the solar system. At that particular time, I was not yet in the space industry, but it was in my mind, and I knew that's where I wanted to go. So the fact that somebody was talking about asteroid mining at that time was just amazing. And I was very excited that they were doing this. There were a bunch of luminaries involved in this company. And you can see some of them listed here: Eric Anderson, Peter Diamandis as founders and co-chairman. Chris Lewicki was the president and chief engineer. The investors included people like Eric Schmidt and Larry Page of Google and Ross Perot Jr. So there were some really big names behind this thing. And that lent a lot of credibility to what was going on. About several months later, another company announced, and that was Deep Space Industries, and a number of very interesting folks involved in that. Both of these companies were talking about extracting resources from the solar system, specifically mining asteroids for metals and what have you. This infographic from Planetary Resources kind of outlines what they were talking about. And it was going to be amazing. We were going to be getting asteroids with rare earth metals like platinum, and that was going to crash the market on the Earth for platinum because it was now going to be so plentiful that the cost of platinum would be pennies per pound or whatever. And they were going to be mining water, and we could use it for propulsion. And this would open up the solar system for settlement, and it was going to be the golden age. Shortly after that, actually this was in 2016, the government of the Grand Duchy of Luxembourg announced a sovereign wealth fund of 100 million euros that would be invested into companies doing space resources. So we have two companies, that makes a market, right? And we have a national government announcing publicly that they're going to be investing money into space resources. So this really sounds like a thing, right? And it was very exciting in those days. And so fast forward to 2018, and we find that Planetary Resources suddenly got sold to Consensus, which is a blockchain company. What does blockchain have to do with resources? I don't know. And then a couple of months later, Deep Space Industries was acquired by another company called Bradford Space. Bradford Space is not really interested in space resources. They were more interested in the deep space propulsion systems that DSI was developing. This is very disappointing because all of the interest and the excitement and so forth suddenly seem to evaporate. So the question arises, does space resources make sense? Is it something that we should be focusing on? And my answer to that question is yes. We should very definitely be looking at space resources. And here are some reasons why. If we intend to expand into the solar system, which I intend to expand human civilization into the solar system, I don't know about you guys, but that's what I intend to do. We need to use the resources in the solar system because it can't all come from Earth. The Earth is a 4,000-mile deep gravity well, and it takes an amazing amount of energy to get anything from the ground into space. And so the less mass that we can put into space, the better. It turns out that a lot of what we put into space is water, or I should say propellant. And I'll come back to that in a minute. But the point is that if we can gather those resources from space, that will facilitate our expansion into space. It also turns out that on NASA's roadmap, they're talking about extracting resources from Mars. So if you know anything about the journey to Mars that NASA has been talking about, they want to send astronauts to Mars. They're going to land the lander on the planet, and then they're going to generate the fuel to come back to Earth on Mars. So that means they got to find where the materials are that can be used to produce fuel. And so that means extracting resources. Ultimately, we can go to asteroids to extract resources for propellant and other raw materials. And finally, the moon will be a critical test bed for these technologies. So I'm going to talk about some of these things and let you understand where the technology is today, what things are possible, and who are some of the people who are involved in doing these things today. So I had intended to have a bottle of water that I was going to drink from, but water is life. Water is air, if you split it into hydrogen and oxygen, and water is propellant, because hydrogen and oxygen can be used for fuel. It also turns out we can use straight water for fuel. So water is the most critical resource in space. And so if we can find water elsewhere in the solar system, that will be tremendously useful. So it turns out that the market today for propellant on orbit is huge. If you take a look at all of the launches that happen every day, or every year, I should say, and add up the amount of propellant that is being launched into space from Earth, it adds up to a total of at least $3 billion per year of resources that are being launched from the ground. If you look at just the fuel used for raising the orbit of the geosynchronous satellite from low Earth orbit to geosynchronous orbit, it turns out that the cost of that propellant is something around $300 to $700 million per year. And finally, the United Launch Alliance has publicly expressed a desire to buy propellant on orbit, and that they are willing to buy 210 tons, which I think actually that should be megatons, I'm not sure, I don't remember, of hydrogen and oxygen per year. And that equates to about $630 million per year from one customer. So if you think about that amount of propellant which is being launched into orbit, which could come from somewhere else, that right there is a huge market which is just waiting to be tapped. So the opportunity is there if we can figure out how to extract the resources from space and actually use them. So I said water is the most important resource. So where is water in the solar system? Well, we actually have very good reason to believe that there are significant quantities of water in the lunar poles, specifically the lunar south pole. But there's, we also believe there's some in the north pole as well. And this isn't showing up very well, but if you look here, all of these blue spots are areas where we have detected the signature of water. And that's water on the surface of the moon. So what form does that take? It's not liquid water. Obviously, the moon is a cold place and it's a vacuum, so it's ice. And whether that water is just on the surface or whether it's mixed in with the lunar surface material is, we don't know. But we know that the water is there. We found water on Mars. In fact, we found a lot of water on Mars. This diagram from the subsurface water mapping project at NASA shows where they believe there is ice, essentially not too far below the surface of Mars. So all of the blue here shows where they believe that there could be water, and this is from the equator to 60 degrees north. So this is only in the northern hemisphere. And it's pretty clear that there's significantly more quantities of water above 60 degrees north as well. For example, we know that the Martian pole has massive glaciers and so forth. But this is water in low latitudes, which means that if you're going to put a colony on Mars, getting water will not be a difficult thing. Very important if you intend to settle Mars. This is my favorite plot of all time. This is a plot of the inner solar system. So this circle here is the orbit of Jupiter. These circles here are the orbits of Mars, Earth, Venus, and Mercury. The Sun is there in the center. And all of these green and red dots are minor planets. So those are asteroids. The green ones are main belt asteroids, but the important ones are these red ones right here. These are the near-Earth asteroids. And there are thousands of them that are actually easier to get to than the surface of the moon. So this represents an enormous amount of resources that we have access to if we just go get it. How much? How much resources is actually there? It's a mind-boggling amount. So this table, which I took from a really excellent book called Asteroid Mining 101 by Dr. John Lewis, who he has seriously analyzed where this stuff is, what the contents are of various kinds of asteroids, and what it would take to actually get that material. So this table tells us how much of the resources are out there. So on the left are the various materials that are necessary to support human life in space, ranging from water at the top, ferrous metals, we'll use that for building things, that's iron, nickel, cobalt, related elements. Carbon, absolutely essential for life. Nitrogen, phosphates, also important for sustaining life. And at the bottom are silicates, which you're going to use for building things, like shelters, radiation shielding, and so forth. The next column shows how much is available. And this is just near-Earth asteroids. So we're only talking about the red dots on the previous diagram. And this is 10 to the 9th metric tons. So 5,000 times 10 to the 9th metric tons of water in just near-Earth asteroids. And you can see the other numbers as well. So if you were to think about how much of a particular substance would be required to support a human life in a sustainable system, so assuming full recycling, and that might be a little optimistic, but let's just bear with me here. Just assume that we can fully recycle everything that we're using. So the third column there shows how much of a particular substance would be needed to support one person essentially indefinitely, because we're talking about a closed system that fully recycles. So given those numbers, then the column on the right shows us how many billion people could be supported from now until the end of the sun, until the sun dies, because the sun turns into a red giant and consumes the inner solar system and so forth. But that's how many people could be supported using just resources in near-Earth asteroids. So the minimum number there is 400. So imagine 400 billion people. That's 40 Earths. I mean, assuming that we have a maximum population on the planet now of 10 billion, that's 40 Earths worth of population that can be supported only by the resources of the near-Earth asteroids. Okay, and if you recall the previous diagram, that was a small part of the resources that are actually out there. So this, my friends, will support us from now until eternity. So this is why we want to extract resources from space. So how do we go about doing that? This diagram is from the Committee for Mineral Reserves International Reporting Standards. And they have defined what are the steps that you have to go through in order to demonstrate a provable reserve. This is important because banks invest on provable reserves. So the inferred resources, we think there's something there. The indicated resources, okay, we found indication that that resource is there. Measured, we've measured how much is there. So the column on the left is just resources, basically the total amount of a given resource that's there. The column on the right, mineral reserves, is how much of that can be economically extracted in a feasible manner. And so you move to what is the probable reserve, and then finally, what is a proven reserve. And banks invest on proven reserves. So here is the problem. This is where we are right now for space resources. We know the stuff is there, we know it's out there, but we don't really know in what form it is or how difficult it will be to extract. This is where we want to get to. We want to make sure, we want to be able to prove that the reserves are there. And at that point, the banks will invest. So we got a little work to do. So how do we find where the resources are? This is a map of lunar geography. And it is based on orbital observation and some information from what the Apollo missions picked up on the ground and various rovers and so forth. All of the colors are showing different deposits, and I didn't put the key up here for what the colors mean, but ultimately it only tells us where the material came from. It doesn't actually tell us what the composition of that material is. So we have some idea based on the lunar rovers that have been there, taken samples, and the Apollo missions. But what we do know is that the moon is covered in regolith. So what is regolith? This is an important word. You'll hear about it constantly when people talk about space resources. So regolith is the loose collection of material that lays over solid rock. And it consists of soil, dust, sand, broken rock, and other materials. It's created by weathering of the solid rock. So on Earth, here, we're familiar with this. There's a layer of soil, there's some material underneath that, and eventually down far enough you get to solid bedrock. And regolith is created by organic biological processes. There's some organic material in there. There's water acting on the rock to break it apart and so forth. So there are a number of processes that we are familiar with that create that. On the right, you see a similar diagram showing what we believe the regolith on the moon is like. And you might say, but there is no weather on the moon. How does the solid rock get weather? Well, it turns out that the things that act on the moon are basically impacts. So ranging from large meteors, asteroids, all the way down to micrometeors. And that basically pulverizes the lunar rock so that you then get a layer at the top, which is fine-grained material, and then underneath that is large-scale ejected. It's kind of mixed in with coarse-grained material. Then you have disturbed crust, and then finally you get down to the intact inner crust. This is a different process than what we're used to. So understanding how the lunar regolith is formed and what it consists of is going to be very important if we want to extract resources from the moon. So this is what regolith looks like on the moon. There's a lot of fine-grained stuff down here. We've got some rocks, bedrock up there, maybe that's been fractured. Over there, maybe you have a crater wall and so forth. So that's regolith on the moon. Here's regolith on Mars. And this was taken by Curiosity. That's why there's tracks there. Those are not aliens. It's Curiosity rover. But notice this. So here you have a relatively hard, compact surface. It's consisting of small fragments with sand-like material in between it. The tracks are not making a lot of impression here. Up there, we have a different material. That looks like sand, and you can see that the rover actually made deep tracks there. So these things look familiar to us. And there is, in fact, weather on Mars. There's no water, at least none that rains. So this is probably generated by the action of impacts like on the moon, but also by the movement of small grains of sand and so forth by the wind. And there was water on the surface of Mars, so there's been some action in water. How much of that happens now, we don't know. Some of it might be glaciers. We have ice under the surface and so forth. So there are some other processes going on Mars that we are still unclear about how they work. So what can we do with regolith? Here's some things we can investigate it. Of course, we want to find out what's there. A lot of opportunity for geology. We can extract oxygen from the silicates that make up the regolith. We can extract water. And as we said before, water has lots of uses. There are other volatiles as well in the regolith. And these include things like methane, helium-2, hydrogen, and so forth. And these things are also important for sustaining a settlement on the moon. And then there are other materials. We can extract metals. We can create glass fibers. Creating things out of the bulk aggregate of regolith is important. We can create berms that you can bury something underneath. That will give you radiation shielding and also give you thermal protection. And so these are very important. And then there are various other things we can do. So how do we use the regolith? This complex diagram just shows some of the different processes that happen. And you want to think about starting up here at the top. We find where the regolith is, so we want to characterize what the resources are. And we need to extract it, transport it to where it's going to be processed. We process it. We then separate it out into the different materials that we need, and you can actually then start manufacturing things from it. So we don't need to go through this in detail, but it's just important to understand that, yes, there's a process of things that have to happen, ranging from the initial exploration, then extraction, processing, manufacturing, and so forth. So in order to do this, there are a number of capabilities that we require, ranging from prospecting to mining. We need to be able to build structures like berms, roads, and so forth. Obviously, we have to extract it, and ultimately, we want to be able to refuel our spacecraft. And this picture right here is worth keeping in mind. I mentioned before that NASA has in situ resource utilization as part of its plan for going to Mars. It's also on the plan for going back to the moon. And if any of you have been watching the space news, you know that NASA has been talking about the new Artemis program, which is our return to the moon. And so that program also will require that we go to the moon, extract propellant so that we can come back from the moon. So all of these things are becoming essential to how we can go into space. these are some of the steps that you would have to go through. I'm going to focus primarily on extracting water because, as we said, water is the most important resource in space. And so there are several steps that we have to go through in order to do that. We have to excavate, we extract, purify, remove contaminants. If you want to create hydrogen and oxygen because you want to use that as rocket propellant, then you have to electrolyze it. Then you have to cool it down so it becomes liquid, and then you have to store it. Most of these are actually relatively well understood on the right-hand side. On the left-hand side is where we need to develop some capabilities. So let's look at some technologies now. At the Space Resources Roundtable, I had the privilege of seeing some of these rovers and other devices that are being developed to actually extract resources from the moon. This is the first commercial prospecting rover developed by the U.S. company, and the company is called Lunar Outpost. It doesn't look like much, but it actually has a lot of capability. The payload size of this is on the order of a CubeSat, so if you wanted to put some experiments in there, that would be possible. It also has a capability to do some drilling into the surface and analysis of the regolith that it encounters. So some more rovers here. There's a company called Astrobotics. They've been developing robotic technologies for space since 2008, and they developed this thing called the Polaris extractor. And the intention here is a device that can scoop up regolith and transport it to a processing facility. It has an innovative side scoop design, so you'll notice the scoop here rotates perpendicular to the direction of travel. One of the challenges of having of these kinds of capabilities on the moon is that there's only 1/6 gravity. So think about this. If I want to move, say, an object like this podium, like that, right? In order to do that, I'm depending on my foot having friction on the ground. And for that friction to happen, my mass is being pulled down by the gravity of the planet so that I'm sticking to the ground. If I have 1/6 gravity, I can't exert as much force. So it becomes more challenging to do things like push large piles of gravel around. And so the side scoop design on this rover helps with that because the direction of scooping is actually perpendicular to the direction of travel. So it helps with that particular problem. This particular design can carry 80 kilograms of payload. In a test, they demonstrated that it could actually move 1,000 kilograms in under an hour, which is actually a significant amount. It could excavate a trench to about 20 centimeters depth, and it can climb the slope to about 15 degrees. So that's a step. We'll see later on that 15 degrees is not that steep of an incline. This is RASER, and this is actually developed at NASA. This is a funky looking thing. So let me show you what you're looking at here. This is the main body of the rover. These are the wheels that actually propel it. And then here are drums that rotate, and if you look, you can see that there are little scoops around the sides of that. So what this thing does is it can travel in a straight line and scoop things by rotating the drums. And so that it fills up the drums, and then it goes and can drop off the payload. You'll notice that the drums are on these arms. These arms go up and down. So here's an example of RASER actually in operation. And you can see that it actually could excavate a pretty deep trench. So it has the ability to move a lot of material. And then on the right there, you see it can reconfigure itself so it can move actually its center of gravity and allow it to climb a steeper slope. So this could actually climb a 35-degree slope. And that's important because if you're talking about going into a crater, the sides of the crater are likely to be steep. So we need to be able to traverse that kind of slope. So this is a very, very interesting technology, and this is the kind of thing that we need to see developed because we need solutions that you're not going to see here on Earth. Okay, so that's collecting regolith. But what happens if the water is deeply buried underground? Maybe there's a layer of crust and there's ice below it. And this is the likely case on Mars, where we may find subsurface ice. And so in that case, you want to drill down to where the layer of the ice is. And then having created a hole, the borehole into the water, into the ice, you can then start to melt the ice. And then once the ice becomes liquid, you can pump it out, then you have water. And then it uses actually warm water, hot water, to melt. So there's sort of a cycle going on as it pumps out the water. So this is a concept for extracting water. Along those lines, a company called Honeybee Robotics, which also develops robotic technologies for space, developed the Planetary Volatiles Extractor drill. So this is a prototype drill which has been tested on actual simulated regolith. So there are regolith models, essentially, and people have created samples of this material and then used this device to actually drill through it. And so they demonstrated that this is a feasible technology, that we could actually drill into the regolith, find the water, or find the buried ice, and then start to extract it. So, if we want to extract ice, we have to go where the ice is. The problem is that it's in the lunar South Pole. The reason why we believe that the ice is in the lunar South Pole is because there are places where the sun never shines. In particular, the one that's been identified most notably is Shackleton Crater, which is pretty close to the lunar pole. The base, the bottom of the crater never sees sunlight. And as a consequence, it's very cold. I mean, like, really cold. 25 degrees above absolute zero. That's really cold. But that acts as a cold trap. And so water molecules enter that cold space, and basically they lose energy, right? And they fall to the ground. And so we believe that there's a whole lot of ice that has been trapped there. Okay, so you're talking about a permanently shadowed region. There's no light. It's very cold. That is a very extreme environment in which to operate. So on the left here are some examples of where we've operated rovers in the past. On Mars, the conditions get down to about 208 degrees Kelvin, which is cold by our standards, but as these things go, it's pretty warm. So that's about the coldest that we've operated at. So there's a need to develop technologies to operate in these very cold conditions. On top of that, there's no light, so there's no way to generate solar power, which means that we'll have to come up with some way of directing energy to those rovers or other machines that will be extracting the ice. You'll notice over here, there's also the persistently lit region. So depending on where you are near the South Lunar Pole, you might be in light all the time, or you might be in shade all the time. But this is an opportunity because it means that here we can put solar collectors and then we can beam the energy into the permanently shadowed region. So here is a proposal for extracting ice from Shackleton Crater or similar places in the permanently shaded regions. And the idea is that you put basically an impermeable tent over the surface. And then you, using mirrors that are up on the side of the crater, you beam sunlight into the tent. And what happens when you shine sunlight on something? it warms up. And so the regolith inside the tent gets warm, and the volatiles, including water, vaporize and come out. And so then we have a cold trap here on the side, which sucks that volatiles into the tank, and then we've extracted water. So this is one approach for extracting water from the lunar south pole. This is a little hard to see. I'm sorry, I couldn't get a better diagram. But this is a rover that basically does the same thing. So instead of having a big tent, you have a rover which has a dome. So here you can see there's wheels of the rover, there's a dome here, this is down on the ground, and it basically does the same thing, but it's all sort of self-contained. Up here, it's kind of hard to see, but it's the same thing with the dome up, so it can move around in different locations. And the concept there is that the rover would move around, find a place where there's, we believe there's a lot of ice, put the dome down, heat it up, collect it, and so forth. So a similar concept, just in a different way. So, assuming that this operation gets deployed and starts working, this is what it might look like. So, up on the top of the crater rim, we have big mirrors. The mirrors are shining sunlight down to your extraction dome, where it then focuses it inside the dome, and then on the side of the dome you have the cold trap, which is collecting ice. So this is quite feasible. There are a number of challenges that we have to address, but people are working on these things now. So we can use similar technologies on Mars, warmer, so we might have a little bit easier time of it. But let's talk about the asteroids. Because, as I said before, it's the nearer of asteroids and ultimately the main belt asteroids where the majority of the resources are. This is a completely different challenge. Here are 3 different asteroids that we've actually been able to visit. And different sizes. Ryugu is currently being visited by the Japanese Hayabusa space probe. Bennu is currently being visited by NASA's OSIRIS-REx mission. And there was I don't remember if it was Hayabusa or a different Japanese space probe that went by Itokawa. In all 3 cases, however, what you're looking at is basically a big pile of rubble, which is held together by its gravity. That's a completely different situation. And one of the challenges here is that because the asteroids are so small, the gravity may be enough to hold the rubble together, but you don't really talk about landing on an asteroid just because there's not enough gravity. You talk about docking with an asteroid or something along those lines. So what does that actually consist of? Well, this is asteroid regolith. This is the surface of Bennu. And it's mostly just homogeneous broken rock. So extracting resources from this is a very different challenge. Here's some of the challenges, right? Microgravity, uncertain of structure. We don't really know what they look like underneath the surface. It's possible that you might sink into the regolith. If you try to land on it, you might kick something. It flies off into space because there's no gravity. It's potentially a very dusty environment. And as you go farther and farther out from the orbit of the Earth into the main belt and further out possibly, you'll have less and less solar illumination. So there are various technological approaches to solving these problems. In microgravity, you have some kind of adhesion to the rock, and you can crawl, or maybe you can hop. And to prevent sinking into the regolith, you just have a large surface area. And then finally, to deal with the dust and limited solar environment, we can use radiothermal generators and mechanical structures which are encapsulated or protected from the dust. So what kind of technologies can we devise to extract resources? Well, here's one solution. This is developed by some folks at the University of Colorado at Boulder. They call it an area of effect soft bot. So this is a spacecraft which has soft materials. So these petal-like structures are actually flexible, and they're able to move kind of like muscles, you might say, or maybe like wings. And so the concept here is that this can land on the surface of the asteroid, and the petals will adhere to the surface through electrostatic adhesion. And then in the middle is an extraction device which kind of just scoops up the regolith and puts it into the bucket, and then when the bucket is full, it boosts it off the asteroid. Low gravity, so it doesn't take a lot of force to do that. And then orbiting the asteroid, you have a mothership, which is basically receiving these streams of rocks that are being thrown at it. And that would then perform whatever sort of extraction might be done. And here's a close-up of the soft bot, just showing some details of the petals and the extraction bucket in the middle. There's some other ideas for extracting materials from asteroids. Optical mining is a very interesting concept. So we were kind of scratching at this when I was talking about using solar power to extract water from Shackleton Crater. This takes that idea to the next step. Basically, it uses solar concentrators to focus sunlight on the target material and cause the volatiles to evaporate, which actually causes falling and just kind of big, you might say it bubbles, but it's solid. It's not liquid. So the concept here is you're focusing the sunlight on the material. It then will excavate essentially the regolith material. The volatiles vaporize, and then they can be captured in a cold trap, and you end up with basically a big bucket of ice. So this is a concept, or a depiction of this concept that's being developed by a company called Transastra. And so Transastra is developing this technology into an actual spacecraft. Now what you see here is what they call the Honeybee, which is a large-scale spacecraft. But they are developing a CubeSat-scale demonstration mission that will fly sometime in the next year or two. And the concept there is that they have this small version of this optical mining system that will go up on a rocket, and then there's a secondary payload, which is actually a piece of rock. And so the rocket will release the rock, and then the mini-V, as they call it, will chase it down, capture it, and then demonstrate optical mining. So this is our long-term goal, is to be able to settle space using the resources that are out there, because it's much more feasible to use what's up there rather than having to boost it from the ground. So, questions?
So, how are they going to build something like the Honeybee out there? I imagine that's pretty large. Are they going to take pre-built components, launch them? Are they going to try and put it together in space? Is it going to be assembled under?
I'm not entirely certain what the ConOps is for the Honeybee. The Mini-V will be launched as a single spacecraft, but we're also developing technologies for assembling larger structures in orbit, so Honeybee could be assembled in orbit.
Yeah, so earlier when you showed the map,
Can you hold it like a little?
yeah, earlier when you showed the map of the moon, and there were certain spots that had more blue concentrations, what did that actually represent? Do we know for sure that that's water, or is it something else that's highly indicative that there is water there?
Right. So the The indications of water are basically from neutron emissions, which have a signature that's characteristic of water. Now, it does turn out that it could be other materials that have an OH, so it could be hydroxylated minerals, but that would require that the mineral be formed through some chemical reaction, right? And so the most obvious thing is it's just H2O. It's basically condensed and precipitated. So yeah, we don't know for sure. Again, as I said earlier, we're only at the indication stage. We have indications that those resources are there, and we aren't going to know until we actually go and look. So really the first step is we got to get rovers on the ground to go look at it.
I was interested in your picture of Shackleton Crater. We've always heard theories about water ice and deep, dark recesses of craters. But that slide showed that the outside of the rim also is totally shielded from sunlight. Apart from the question of getting energy there, is there likely to be any difference in the quality, quantity, or accessibility of water deep in the crater or on the shady side of the mountain?
That's a very good question, actually. And I didn't create a slide to show that, but the slopes on the edges of the Shackleton crater are like 35 degrees, so it's like that much of an angle. And so we believe that it's inside the entire crater, right? So there's going to be stuff at the bottom, there's going to be stuff on the sides. The challenge is going to be how do we traverse those kinds of slopes. Now, the other part of your question is that maybe there's water outside of Shackleton Crater as well. And we know, I mean, Shackleton Crater is a big place. It's 24 kilometers across. But there are other craters as well that have similar properties that are nearby. I would not expect that there would be permanently shaded regions that are not in a crater, right? But there are other craters nearby as well.
Will the quality of the water and the quantity and the accessibility be about the same on the outside as down at the bottom?
Well, H2O is H2O, right? Yeah.
Icebergs on the side versus pools at the bottom. I mean, is that...
Yeah, it's a good question, and the answer is we just don't know. We have to go and look.
So, this is in terms of water and other materials in general, but do we have any foreseeable technology that deals with the issue of irradiated materials where we may have to protect against radiation poisoning in terms of our own health bodies, or if we're using it for material that may come in contact with living life forms?
Are you asking about materials that are exposed to the radiation environment becoming radioactive?
Well, essentially, if it's going to be in outer space, that it may risk exposure to some kind of radiation.
Right.
Do we know how to process and purify materials that may end up in contact with human beings?
3 feet of dirt.
Is it as simple as that?
Yeah, pretty much. And if you were here several months ago, Michael Chalmers-Dunn was talking about building habitats in lunar lava tubes for exactly the same reason, because then we don't have to extract holes in the ground to live in, right? The lava tubes are already there, but the point is they're underground, and so they'd be protected from the radiation environment. But yeah, one of the uses of regolith in general is just to pile it up and bury stuff in it so that it's protected from the radiation environment.
So I'll skip the joke about heavy water being radiated, the benefit there. So could you remind us of the mission that had an impact spacecraft to look for water to disturb the surface?
Right.
I don't remember if it was on the moon or Mars.
No, it was on the moon. So the L-Cross mission was orbiting the moon, collecting various kinds of data about it, and then when it reached the end of its life, basically meaning it ran out of propellant, they intentionally crashed it into a location near the lunar South Pole. So that was the mission, and when it impacted the ground, it kicked up a bunch of stuff, including water. So that's one of the pieces of evidence leading us to believe there's a lot of water there. Yeah.
Hey, Dave. Great presentation. If I quit my job tomorrow, it's your fault. But one of the interesting things, one of your first slides said that the estimated fuel to just the differential to get up to geostationary orbit was up to $700 million a year,
Right.
if I recall. And ULA was offered to buy up to, what is it, 630 million a year.
Right.
If the U.S. represents something less than half of all geostationary satellites, which a quick glance at Wikipedia looks like it's about that. So let's figure, basically, ULA is looking to spend a lot more to buy a lot more water than the market could bear for at least the U.S. market. So what does ULA know about the space economy's development that the rest of us don't know?
That's a really good question, actually. So ULA has been developing a propulsion system called the integrated fluid, IVF, integrated vehicle fluids, which is entirely based on liquid hydrogen and oxygen. So that's what they want the water for. And when that, it's called ACES, and when that will fly, we don't know. It should be flying in the next couple of years. But that was the goal, was they wanted to buy propellant in order to fuel ACES. And ACES was intended to operate on orbit on a long-term basis. So it's not a one and done. They would launch it and use it to shuttle things around, and it would have to be refueled. So that's why they want to buy all the propellant. So I give ULA as an example customer, right? Because that demand is not there right now, but they've expressed this publicly as they're willing to do that. So we expect that demand to develop in the next couple of years.
How far along in the infrastructure development process do you think it would be useful or necessary to actually send humans into space, or would it all be done robotically, do you think?
So the long-term purpose is for humans to go, obviously. Initially, we're going to have to depend on robots just because the environment is so extreme. I mean, I did show an image that had some astronauts in the floor of Shackleton Crater, but I wouldn't want to go there, it's too cold. So yeah, a lot of this will be done robotically, but we need to have people nearby operating the machines. So, I mean, NASA has done some great things with the Curiosity rover. It operates autonomously millions of miles from Earth, and so it gets instructions on an irregular basis or not very frequent basis, right? But if you think about the amount of geology that Curiosity has done in the 7 years that it's been there, that amount of geology could have been done in about 3 months by a human geologist. So that's kind of what we're dealing with, right? So yeah, we're going to go with machines, but ultimately we'll have to send people. How, what the timing of that is unclear at this point.
Can you talk a little bit about how much fuel it takes to change the orbit of a near-Earth asteroid to make it accessible near Earth?
Well, it's near Earth, so I don't need to change its orbit.
Actually, you do. It's not in orbit around
It's
Earth.
not in Earth orbit, right? It's in an orbit that's near Earth. And you're right, it could go to the other side of the solar system, but really there's no reason why you can't put your ISRU operation on the asteroid and to extract the materials, then those get sent back to wherever you're going to use them. And that's not necessarily Earth, right? That's going to be orbital manufacturers and so forth. So yeah, I don't expect that we will be changing the orbits of the asteroids. We're just going to be taking stuff off them until they're not there anymore.
But that requires the same amount of energy.
Over a longer period of time. Yeah, and some of the things that you're extracting are propellant that you're going to use. So yeah, what exactly the delta V's are, it's in the range of probably 3 to 5 kilometers per second. So how much propellant that would be depends on the mass that you're moving. Any questions?
In one famous science fiction story, I forget whether it was by Heinlein or Asimov, they were basically dropping water asteroids onto Mars. Is there any indication prediction that any of the stuff floating around Saturn or Jupiter will be all ice? Or is that just still science fiction, that there might be something like that out there?
Well, like the rings of Saturn we believe those are largely water.
They are basically largely water.
Yeah. It turns out actually that water is really everywhere. Everywhere that we've looked, we find water. So the asteroids are, I mean, it depends on the type of asteroid, but they all have water on them in one form or another in varying quantities.
So if there's a case where long-term we may want to send those, change their orbits if we have enough energy to bring them closer. Long-term.
Sure.
At the right time.
Sure. Well, and just as you're talking about science fiction stories, if you're watching The Expanse, you may remember in season 1 of The Expanse, the Canterbury, which was the spacecraft that our heroes started out on, was explicitly mining ice from the rings of Saturn and to bring it back to Ceres. So yeah, we'll want to push water around the solar system for sure, and other materials for that matter.
So at the beginning of the presentation, you talked about how, like, for example, the price of platinum could plummet greatly just by sourcing materials from outer space. So have you ever thought about or worried about what the economic impact might be if we start, flooding mass amounts of all kinds of materials back on Earth?
Right. It is a significant question. And I have two answers for you. The first one is that a lot of those materials actually will not come back to Earth. They'll stay in space because we'll use them to build habitats and other things, right? The other answer to that question is, let's say 150 years ago, aluminum was an extremely valuable material. So valuable that they put the top of the Washington Monument was made out of it, and Napoleon had gauntlets made out of aluminum. And so then they discovered a process for refining aluminum that was cheap. And so the price of aluminum crashed, right? So did that cause an economic crash? Well, not really, because now we discovered that we can use aluminum for all kinds of amazing things. And so I think that is probably more the scenario to think about. Right.
Just
So,
in the extended, the more extreme case where multiple or almost all things that we considered valuable previously are all of a sudden cheaper than they're quite literally.
then we'll have amazing new capabilities.
Yeah, it's good. When the insertion factors economically are low, then the value-added amount can be...
So just don't expect to store your wealth in gold. Maybe blockchain tokens, I don't know.
The story of aluminum is maybe illuminative. There was the guy who invented aluminum 2,000 years ago. The alchemist brought it to the king, and the king had large gold reserves, and so he killed him. And nobody figured out how to smelt aluminum for another 1,000 years.
It requires lots of electricity.
Does that mean David's going to get a bodyguard here?
That's Steve. So one of the things that PRI was doing originally, one of their first business phases was going to be to develop, as I recall, prospecting using like 6U CubeSat formats, I believe Planetary Resources.
Yes.
So looking into that. Has anybody picked up the torch on that? Because that's like the next level of prospecting beyond the slide with all the red dots. So is anybody kind of picking up the baton? I know the B612 Foundation wants to do it for other reasons, looking for earth grazers and things like that, but is anybody looking at that?
So in terms of actually prospecting asteroids,
Yeah.
no, I don't think anybody is doing that right now. The focus right now is really on the moon. And I mean, the moon is right there and somewhat easier to get to. So yes, we'll have to go back and do that. I personally think that DSI and Planetary Resources were a little bit early in their focus on asteroids. They should have been focusing on the moon. But that's what the second wave is all about. Any more questions?
Is there any one company that's leading the second wave right now?
So I mentioned several companies. Transastra is probably the one that I would say is the most high profile, and they're the one with the honeybee extraction system. But there are a number of others: Orbit Beyond, Lunar Outpost, Deep Space Systems, not Deep Space Industries, Deep Space Systems, and yeah, there are a few others which I should be remembering, but I'm not right now. So yeah, and that actually was one of the things that impressed me a lot at the Space Resources Roundtable, was really how many companies there are that are working on this stuff right now.
Which do you think will come first? The technical ability to harvest lunar resources or the legal right to do so?
And I'll punt that question to my friend Charles Glenn.
Very good question. Very good question. And I think that, the different countries and the international community are debating that. The United States and Luxembourg would say that they have the rights now to extract the resources. The United Nations would say, at least with the Moon Agreement, they don't. So we'll see how that plays out. But right now, I think that it is, and it's going to have to head that way. Nobody's really going to stop it at this point.
Great, well, thank you all for coming out.
Thanks very much to you, Hurst, for a great presentation tonight, and remember, November 14th, put it on your calendars for the next New Space Chicago event. So thanks everyone for coming by tonight.